Hello everyone, this video is going to go over the homework problem from Tuesday night, number 46 in chapter 8 of the textbook. So in this problem we've been given sort of a modified Atwood's machine. We have a double incline with the rope hanging over the pulley, and we are first asked to draw free body diagrams for each of the two blocks and for the pulley. So if we look at block A, we know that it has its gravitational force pointing straight downward. We have the tension pointing along the incline at a 32-degree angle, and the normal force pointing perpendicular to the incline. And since this is a frictionless surface, there's no friction. And also notice that we were told that the blocks move toward the right. So block A is moving up the incline. So we know we want that to be the positive direction. Similarly for block B, we have its weight down. We have tension B pointing up along the incline to the left at a 61-degree angle from horizontal. And we have the normal force perpendicular to that. And finally for the pulley, remember here we're dealing with something that rotates, so we're going to have to consider not only what forces act on it, but also where those forces are applied. The key thing is that both sections of the rope must leave the pulley perpendicular to the parallel to the surface of the pulley. So tension A points like this, tension B points like that. But the critical thing is that in both cases, the R vector will make a 90-degree angle with the force vector. Notice also for block B, we know that it goes down the incline, and so we would want to make that the positive direction. So that gives us our three free body diagrams. We're then asked to find the tension in each of the two ends of the string. Notice here that we have been given the acceleration, and so finding the acceleration is relatively straightforward. We don't need to involve the pulley in that. In both cases, since we know the acceleration points along the incline, we would want to rotate the free body diagram just like we did earlier in the year. So if we look at block A, we rotate it so the normal force points upward. The tension points to the right, and then we have the gravitational force at a 32-degree angle away from vertical, and the direction to the right would be positive. So if we look at the net force in the x direction on block A, we know that equals the mass of block A times its acceleration. We also know the accelerations of the two blocks must be equal because they're connected by a rope of constant length. Looking at the rotated free body diagram, we have that FTA minus m sub a times g times the sine of 32 degrees equals mass of A times the acceleration, or the tension in string A equals the mass of block A times the quantity G sine 32 plus A and plugging in all of those values. Mass of A is 8 kilograms. G is 9.8 meters per second squared. And we are given that the acceleration of the blocks is 1 meter per second squared. We then get that the tension in the left-hand side of the string, FTA, equals 49.55 newtons. Similarly, we would rotate the diagram for block B. Again, rotating it so the normal force points straight upward. That would make the tension FTB point to the left. And the weight of block B will point 61 degrees to the right of straight down. And we know that to the right or down that incline is the positive direction. So again, we set up a Newton's second law equation, this time for block B. Here the net force is mass of B times G times sine of 61 degrees minus FTB equals m sub B times A. Rearranging that to solve for FTB, we would get mass of B times the quantity G sine 61 minus A, and plugging in all our known values, including that the mass of B is 10 kilograms. We will find that the tension in the right-hand side of the string, FTB, equals 75.71 newtons. In part C, we were asked to find the net torque on the pulley and to determine the pulley's moment of inertia. I forgot earlier in the free body diagram for the pulley, there are actually two other forces. We would have the weight of the pulley pointing downward. We would also have a normal force, not necessarily straight up in this case, due to the different angles at which the tensions point. But in any case, both of those forces are exerted at the center of the pulley, which is also the pivot point, and so neither of them is going to exert any torque. The only two torques that we have are from FTA, which provides a counterclockwise or positive torque, and from FTB, which provides a clockwise or negative torque. Both of them are exerted at a distance of 1 radius away from the pivot point, and as we mentioned earlier, the R vectors and force vectors form 90-degree angles for both. And so the net torque is equal to the torque from A plus the torque from B. So for the tension FTA, again, it is the radius of the pulley times FTA times sine 90. We note that's positive because it is a counterclockwise torque. For B, it is a clockwise torque, so it's negative. Radius of the pulley times FTB times sine 90. Sine of 90 degrees is 1. We can factor out the R. And plug in the given radius of the pulley of 0.15 meters. We have the values of FTA and FTB that we found earlier. And you may notice I had a sign error in my answer on the assignment sheet. The net torque is clockwise or negative 3.924 Newton meter. 3.924 Newton meters. We also need to find the moment of inertia. We know that net torque equals I alpha. We know how alpha and A are related since the rope is passing over the pulley without slipping. One thing we do need to be careful of, though, are our directions. Here our acceleration A is positive for the blocks moving to the right, but notice that that causes a clockwise or negative angular acceleration. So we just need to be careful to get our signs right. That A, in this case, equals R times negative alpha. If we don't include that negative sign, we'll just end up with a negative value for I at the end. We know that I needs to be positive, so we could correct it there if necessary. This means that alpha, in this case, equals negative A over R, or net torque equals negative IA over R. We're looking to solve for I, so we multiply by negative R, divide by A. We get negative R times the net torque over A, or plugging everything in, negative 0.15 meters times negative 3.924 Newton meters all over 1 meter per second squared. And that gives us a value of I of 0.589 kilogram meters squared.